Okay, so basically the reason that we keep talking about logic is that I hope that it will help you understand what you're writing and how to write it, because there is a deep connection between queries and logic, and relational algebra and logic. So I just want to kind of talk a little bit about this because the database semantics is really based on logic. So you have sets of tuples. And if you think about that, you can represent a database as a statement of facts. So logic and databases. So the database content itself generally is called the extensional part of what is true about the world with respect to the specific data model. So basically, logicians will say instead of a database instance, they will use the term extensional database, which is going to be a set of facts, right? I'm going to represent each fact as a statement. So for example, something like, I have hero 1, Captain America. I looked it up, but I don't remember his name. All right, Steve Rogers, thank you. All right, we will write only a couple of these. Hero 2, Iron Man, Tony Stark. What is Agent Carter's first name? Peggy, all right. So on and so forth. So, okay, you have no idea what I'm writing. That's great. So think of these as each one is a statement, right? So basically, we have a schema. Our schema was that you had hero ID, name, and real name. And given the schema, you have a set of facts that tell you that it is the case that Captain America is a hero, it is the fact that Iron Man is a hero, and so on and so forth. And then you have other tables. You can write other statements for those. So you can have, for example, that there is a movie called Captain America with movie ID 1. Let's say there's a movie called The Avengers with movie ID 6, and that there is, tuples in, let's say, hero in movies, that 1 is in 1, 1 is in movie 6, so Captain America is in movie 6, and Tony Stark is in movie 6. Is Agent Carter in The Avengers? No, right? So basically the idea is that my database is a statement of fact, so what is true? So now I can write queries to describe new relations, new concepts based on these, right? So for example, you can find heroes that are in the movie Avengers. So, for example, I can define a new relation called hero in Avengers. Okay. So I want to define a new concept that I want to say hero X is in the movie Avengers, and I'm going to write it based on the facts. So I'm going to say that this is the case if, let's call this A X is a hero. So I'm saying that find a way to map A to an ID, X to a hero, and the last variable I don't care, right? So that's a don't care. And find a, let's say, movie Y, no, let's call this B and Y. Okay, so find a movie B and Y such that, well, actually not Y, because we know which movie we want. We want the Avengers. Right? And I guess I really don't need a Y here. So I want to know if a hero is an Avengers. If the hero has ID A, name X, which is what I will return. The movie has ID B and the value Avengers. And there exists a tuple for hero ID A and movie ID B, which of course is no longer readable here. Okay, I'm going to write this again. So H in Avengers of X if A is a hero with name X, B is a movie with name The Avengers, and that the A is in movie B. Okay? So basically the idea is that, in fact, any query that you can write using relational algebra can be written using logic like this, right? This you can read in many ways. You can say that I can prove that X is a hero in Avengers if you can find a tuple, a fact, that A and X are in the hero, and another fact that B is a movie where the name is the Avengers, and that there is a tuple with A and B, right? So there exists a tuple in heroes, a tuple in movies, a tuple in hero in movie. With these properties, then then this is the case. And or you can just basically say that find one tuple for each of these, and for that return an X. So you can also read it either way. Okay, and this is generally like the prologue notation, or you can also write it like this. Of course, both are the same. Right? If this is true, then conclude that that is true. So you can actually write all of relational algebra using data log. Okay? So this is called data log. Okay? And data log is not prolog because there is a restriction that you can only have simple variables here. Right? So you can only have variables A and B, but you cannot have f of A or s of A. Okay, so that becomes first order logic. First order logic is very difficult, but there are very strict rules in data log that makes it actually computable and efficiently computable. So just to show you the relational algebra versus data log. Because I keep hearing how much you hate Prolog, so I wanted to show you that it's actually databases, so it doesn't suck. That's all I'm trying to accomplish. I actually wrote a whole prologue in Prolog when I was a grad student, but obviously that's a few years after your point. So let's say I have a relation RABC and a relation SDEF, right? Just as an example. So for example, if I were to write that A is equal to 5 of R, right, selection, so this is select, I can write the same thing, and let's call this X, right? So I can say XABC is equal to is RABC such that A is equal to 5. Or you can write it R5ABC, right? So, or you can say X is ABC if R5BC, but if this is 5, this is also 5, right? Either way is fine, it's the same statement. If you wanted to do projection, so if you say x is equal to pi, let's say select a and b from R, so then you can simply say x of AB is R ABC, right? That is projection. Let's do join. So let's say R So if you want to join on A is equal to D from R and S, that is like saying you have A, B, C, D, E, and F if you have R of A, B, C, S of D, E, F, and A is equal to D, right? So this kind of shows you what join is, right? Join is basically one tuple from here, one tuple from here, making that they are the same. Yes? A, B, C, D, E, F. What do you mean? Oh, you mean like also have A and A here? No. No, because this is saying that select all tuples where the A of this is equal to D of this, right? So this is what I'm saying, that find a tuple in R, find a tuple in D, S, and if A is equal to D, then produce a Y tuple, right? What other things do we have? So we have, for example, intersection. Okay, so if you say T is equal to R intersect S, okay, you can simply write that as T of, let's say, ABC is if R of ABC and S of ABC. Okay. You can also write this as R of ABC, S of DEF, A is equal to D, B is equal to that, it's the same, right? Logically, it's the same statement. Union. So if you want to say, let's call this W, R union S. Okay. So I can write that as W of ABC is R of ABC, bless you, or W of ABC is S of ABC. Okay. You see how DEF, for example, the attribute names are irrelevant, right? Because these are variables. So this will match to any actual value that is stored. So they are now just placeholders. Okay. Renaming is obvious, right? You basically write a new relation with different names. It's not even relevant at this point. And then set difference. Okay, this is the last one. So if I have R minus S, so you can say V of A, B, and C is true if I have R, A, B, C, and not S, A, B, C. Okay. Now the last one is a little tricky, so this is not as simple as the others, because you have to define what this means. So not SABC has a very simple assumption, okay? SABC is not true for anything that is not in S, right? SABC is true if it is in S. But you cannot really say things about, random things. Like, for example, is it true that S of Joe, unknown, unknown, false or true? You cannot do that. So generally, this is only defined when you have a value for these. So given a constant A, B, and C, I can check to see if that's in the database. If it is not, I can say not is true. Okay? So this is only defined for certain statements that are considered safe. So this is considered safe because all of these A, B, and C are actually bound in another relation. So I can actually find A, B, and C from this relation, then check that it is not in this one. So generally speaking, negation is actually kind of tricky. You've all learned about negation, right? It's bad. So in this case, this is called the closed world semantics. That I can only check for specific tuple if it's in S or not, and only for those I can execute this. So that's why data log is decidable, because you are not talking about things being incorrect in general, just not being in the relation, right? So this just means that for a single value, an assignment of variable constants to these, if it is not in relation, then this is true. So given all this, relational algebra and logic, you can write exactly the same set of queries. Okay, but there are things you can do in data log that you cannot do in relational algebra. Right? What can you do in data log? What can you do in logic in general? What is it that we all love to do? That when we learn, we try to use it every possible place? You can do recursion in data log, which you cannot do in relational algebra, right? There is no recursion. So you can actually define relations recursively. So for example, you can say in same universe, this is the thing that my husband took, tried so hard to teach me. So let's say two heroes are in the same universe if they are in a, let's say, movie together, right? So you can say that if they're in the same movie, then they are in the same universe. So you can say hero in movie X and Z, and hero in movie Y and Z, and X is not the same as Y, right? If two heroes are in the same movie, then they are in the same universe. But it is possible that two heroes can be in the same universe but not in the same movie, right? But it is possible that this person is in the same movie as that one, this person is in the same movie as that one, then because of that they are in the same movie, right? So I can write something a little bit more, so I can say in same universe X and Y, if, this is a very long predicate name, X and Z, and in same universe, Z with Y. Right? So in ProgLang, you learned that this is a bad recursion, right? This kind of explodes in terms of complexity. But you can do recursion in data log, you cannot do relational algebra. You can actually do recursion SQL. So it really helps to understand how to do recursion properly, to do it in SQL, but that's not universally implemented. The last time I checked, it was not implemented in Postgres, but maybe by now it is. So generally speaking, that you can do everything in relational algebra that you can do, everything you can do in relational algebra, you can do in data log, but not the reverse, right? In relational algebra, you can find if something is true for two tuples in a relation or three tuples in a relation, but you cannot do that in, but you cannot find how many tuples it is true for. So you cannot count arbitrarily in relational algebra, right? So no recursion in relational algebra. And you cannot count in relational algebra. You also cannot count in logic, okay? So you cannot say that there are 5 tuples. You can say if it is at least 3 tuples or if it's exactly 3 tuples, right? That has some property, because we have done find 2 tuples that have something. The same thing is in logic, right? So you cannot count in relational algebra or logic. But in real life, we find that counting is a very important way of, answering certain queries. So we are going to try to find ways to extend our horizon and go from this kind of very basic logic-based relational algebra to something a little bit more close to what we are going to do in SQL. So I'm kind of trying to walk you through logic to a little bit more interesting stuff. And then from there, we're going to move to SQL and the second part of the class. But any question about this? So obviously in data log, there is no cut or fail like you have in Prolog. That's more of an implementation issue. This is you're only trying to describe what is true by using these rules that, based on the intentional data, the extensional data creates new relations. And ultimately, that's what all the queries are doing. Okay, so now let's return to reality. All right. So if you ever talk to people who work in database industry, this is a very cool thing to learn, how they basically sell you something that they've done as a bug as a feature. Have you ever said that, oh, my program has a bug, but it's a great feature actually. This is kind of what we are going for. So in reality, we talked about that relations are, that's a logical statement. It's a set of tuples. So we said relations are sets of tuples, and that by default all relations have a key because in the worst case all attributes in a relation form a key, right? Because of the way we were describing things, right? So as a result, all relations have a key. Well, so database implementers said that, well, that will actually be very expensive to execute if I actually made it so that I force every single query to produce no duplicates. And in fact, customers don't want this. As a feature, I am not going to implement that. Instead, I'm going to implement a bag. Instead of a set, I'm going to implement a bag of tuples. And I'm not going to force that all relations have a key. Instead, I'm going to say, if you want, you can define a key. You can define a key for each relations, but you are not required to. Since you are not required to have a key, that means that relations may have duplicate values. So you can, in fact, have, so let's see. So you can have a relation like this, which technically is not, it actually has 4 tuples, whereas we would, in relational set model, we would say there are 3 tuples because the last 2 are the same, right? But in relational data model, we don't care, right? Honey Badger don't care. So if you want duplicates, sure. If you didn't want duplicates, then you should have defined a key, okay? So this is kind of an important terminology that you have to get used to. A bag versus a set, right? And unfortunately, there is no specific notation for bags. I don't know, some people implement some or invent it. But as a bag, 1, 2, 2, and 3 is a bag of 4 values. That is not the same as a bag of 1, 2, and 3, right? They are not the same thing because one contains 4 tuples, other one contains 3. Whereas in a set, This is the same thing because 1, 2, and 3 are facts. It doesn't matter to me if you state 2 is a fact 2 times or 1 time. So from this kind of logic-based version, we are going to move to kind of a reality-based version where you basically can repeat the same thing. If you did define a key, you cannot have duplicates, right? But if you didn't, this is possible. But because that it is a bag, doesn't need to change what we do. In fact, databases are still implemented in relational algebra. So ultimately, it's a relational algebra for bags. So it is not really so fancy, but I will just show you a few things so that you can start thinking about what will happen in SQL. So the relational algebra for bags basically will kind of extend naturally from what the set version does, right? So if you have selection, projection, renaming, join, these are all exactly the same as before, and Cartesian product, of course. Just that if you had duplicate tuples before, you may have duplicate tuples after. So like in projection, you remove duplicates by force. In this case, you won't, right? Just don't remove duplicates. The more interesting thing is what happens with the set operators. So instead of set, we are going to have bag operators. Okay? They look the same. There is no difference. But let's say you have tuple T is both in R and S. So let's say you have a tuple T that is in both relations, but you can have multiple copies of it. Suppose you have R has m copies of R, of T, and S has n copies of T. Right? So multiple copies of the same tuple. So let's see what happens with the operation. So if I have R union S, then you take the bag union, then you will actually have m plus n copies of this tuple. Right? So you have a shopping bag, 2 shopping bags, you take 1 shopping bag, throw it in top of the other shopping bag. That's what bag union is, right? It's actually that simple, right? You had 2 apples here and 3 apples here, so when you join them, there's 5 apples, right? Stupid as it is, that's what it is. Okay? That's why it's called a bag, all right? So if you did an intersection will only try to find how many copies are in common. Okay? So how many copies are in common? Minimum and even n, right? Okay? So the negation. So again, you have 5 apples. You subtract 3 apples from that. You take out 3 apples. You have 2 apples left. Is this too insulting for you? Okay. So how many apples do you have left? M minus n. Except, can apples be negative? No. Right. So this is the thing that I always do wrong. Does that sound correct? I'm known to mess this up. Right? M minus n, but you know it cannot be negative. So if it's negative, you of course will have only 0. Right? So if there are 0 apples and 2 apples, then you will still have 0 apples. too insulting, I apologize. Okay, so basically, we will add one more operator. Duplicate removal, which I think is a delta. It looks like sigma, but it is a delta. Okay. So the idea is that you can take a relation and remove the duplicates to get a relation without duplicates. So now you can take any of these, and at the final step of duplicate removal, you will get the set operation that you had before, right? So you can go between the two because of this operation. So far, this is pretty boring, okay? Except that kind of keep the bag operations in mind with, you know, thinking about shopping. All right, so this was a question somebody asked like very early when I was doing relational algebra, that you can do a little bit fancier projection. Okay, so instead of just projecting what is in a relation, let's say you have A, B, and C, you can actually project combinations of tuples. So you can project, for example, A plus B, meaning that for each tuple, take the value in A, take the value in B, add them up, get a new value. You can also even rename that. Let's call that D. Okay, or let's add a D here, or let's add an E here. Okay, you can take the value of C, concatenate with E. This is the SQL concatenation, and call that F. Okay, we didn't do that. We couldn't do that before. You could return a constant called foo. Let's call that G. So I added a new column G. All that it has is a single value called foo. Okay. Then I'm going to return column E. And I'm going to return column E for emphasis. The second time I return, I'm going to give it a different name. Right? So the point is that you can project, but when you're projecting, all you want to do is for each tuple in R, you project a new tuple. And in that tuple, you can add new values, you can repeat values, or you can combine the values for that tuple to produce a new column. Okay? So it's kind of called extended projection. It's kind of obvious semantics, but this is really what we are going to be doing in SQL. And outside of these, we are going to add two new, very different operations. Okay, so one we are going to call, well, actually, I'm going to do one more. Okay, I'm going to talk about this, but I'm not going to do too much examples. We are going to add something called outer join. So outer join is kind of a tricky thing, so I want you to see it first. We are going to use it like hell in SQL. Okay, so what is inner join, right? So let's say you had so we generally define inner join as basically take a tuple from R, take a tuple from S, and then you have some join condition. If it satisfies, produce a new tuple, right? So this is your join condition, some sort. And this part is just what we call inner join. So what this means is that any value that you return x, in X, there is a tuple in R and a tuple in S that satisfies the join condition, right? With me so far? Okay. Well, what happens to all the tuples in R that really cannot find a match in S? They're gone, right? So in outer join, you actually add those in. So you can say, how about those tuples that nobody cared about, that they were the A, B, and C, such that there was not any S, D, E, F, where A is equal to D. Right? So there was no S, D, E, F. Or you can write this slightly as, I can write it in a couple of ways. So for these tuples, there is a tuple in here, but there is no matching tuple in S. So I want to return those also. And those tuples have an A, B, and C value, but no matching S value. So I'm going to return null values for these. Okay. And how about the other side? I can say the same for the other side, that I have S, D, E, F, and not R, A, B, and C, such that D is equal to A. So for these tuples, you have an S value but no R value. So in that case, I'm going to return null, null, and null, and D, E, and F. Right? So this whole X here, which is inner join, union, left join, union, right join, is called the outer join. So everything in this X is called the outer join. This is not exactly right because, generally when you see logic, you expect it's a set semantics, but this is actually bag semantics, but it's easier to show it like this. Okay? So it's a bag semantics, except that everything in R that doesn't join with S produces tuples, and everything in S that doesn't join with R produces tuples. And if you want, sometimes you're only interested in these two. That means everything in an inner join and things from R. These two are called the left join because you have R and S, so this is left, this is right. Or sometimes you're interested in these two, they are called right join. Okay? And all three of them is called outer join. So when we do SQL, this is going to become very important. So there is actually a relational algebra operator too, and it's something like this. Like this, which I cannot possibly produce in LaTeX, so I decided to skip it and leave it to SQL. Okay? And two more, then we'll give a short break. So the more interesting stuff is that I can aggregate. I can take all the tuples in my relation, and I can apply an aggregate over some of them. So I can find the minimum value stored for column A. Let's call that D. I can do sum of like this. Okay. Over R. So let's show what that would do. So if you have A, B, and C, you have 4, 5, 2, 1, 0, let's say 2 and 3, and you have 3 and 4 and 5. Okay? So if this is R, X is going to have how many attributes? True. One is called a D, the other one is called an E. How many tuples will there be in X? only one tuple, right? One tuple that will have for D the minimum value of A, which in this case is 2. And then for E, it is going to find the sum of the multiplication of these two. The sum of 2 times 3, 4 times 0 times 5, and 3 times 4. 12 plus 6 is 18. Right? So the aggregation basically will go through the relation and basically apply operations to a column, right? So one could be, it could be minimum, maximum, sum, average, standard deviation, median. Actually, median doesn't exist, but maybe it does by now. But you know, lots of operators, but it basically takes every value and then outputs something. Okay. So you only get one result, but often you don't actually want that. You want to be a little bit more specific. In that case, what you can do is you can do grouping. So instead of aggregating through the whole thing, you can first group by some attribute. Meaning that you find equal values for that attribute. And then you aggregate only within each group. All right. And I'm going to use the same exact notation, but it's going to look like this. So I'm going to first write like this. Okay. Then I'm going to read this as group by A, and then compute these for each group. So then you use grouping. Those of you who know SQL, this is the group by. You basically produce one tuple for each group. Okay? So you will produce one tuple for each group. Okay, so let's see an example. Okay, so let's say that I have R, A, B, C, and D. So first I group by A, right? Group by A, which would mean that I will have 3 groups of this. So I will have a group for A is equal to 1, which will have 1, 1, 1, 1. I will have a group for A is equal to 2, which I will have these 2 tuples. And I will have one group for 3, which will have 3, 4, 2, 4, 3, 5, 1, 1, and 3, 6, 3, 2. Okay? So now for X, I'm going to produce one tuple for each group, right? So one tuple for each group. And in X, I have A, min of B, because I apparently did not remember to rename these, and sum of C times D. Okay. So for the first group, A is equal to 1. Min of B is? Min of B in here is 1. And sum of C times D is 1. How about here? When A is equal to 2, this is 2. The min of these two, right? And this one is 4, right? 2 times 2 plus 0 times 2. For A is equal to 3, this is 4, and this is 6, 15. Thank you. Right? So you produce one tuple for each group. Okay? So right now, we are seeing this just so that you see what these operators do, but you are not going to be required to write back relational algebra, but I want you to understand what they mean because we will use the same operators in SQL. So, any questions so far? Okay, so let's remember a couple of basic points. Relational model, set operations. The relational algebra for sets is identical to data log. Okay, same queries, you can write either one. But in data log, you can do recursion, which you cannot do in regular relational algebra or bag relational algebra. Okay, relational algebra, bag or set, you cannot count unless you introduce this counting operator, right? With just logic, you cannot say there are 5 tuples. It's a very important limitation. So relational databases will implement a bag semantics, meaning do not remove duplicates unless I ask you to. So each bag relational algebra operator takes an input, possibly duplicate value, and it produces potentially duplicate values unless you have duplicate removal, right? Or group by, because group by will always also produce a single tuple, right? You can never have duplicates produced by group by or aggregates or duplicate removal, but the others may or may not, right? So let's stop here, give a break. I have your quizzes here. Please take your exams back. And then we'll start with SQL after the break.